All right, let's talk about something you use every single day but probably never think about. It's the magic happening inside every single one of your chargers. We're diving into how the power from your wall gets converted into the power your gadgets actually need. It's all about AC to DC conversion. Let's get right into it. So here's the thing that might sound kind of weird. The electricity coming out of your walls, that's AC, or alternating current. But take a look at your phone, your laptop, pretty much any electronic device you own. They all need DC, direct current, to run. So what gives? How on earth is this possible? How do we bridge that gap? Well, that's exactly what we're going to unpack today. Okay, to understand why we even have this AC/DC mismatch in the first place, we've got to go back in time. We're talking about one of the biggest, most famous rivalries in the history of tech. This was literally a war over the future of electricity. Picture this. It's the late 1880s. In one corner, you've got the famous Thomas Edison, and he is all in on DC power. He's convinced it's safer. But in the other corner, you have Nikola Tesla and George Westinghouse, and they're betting everything on AC. Now, Edison had a point about safety, but AC had this one killer advantage. You could send it over huge distances without losing much power, and that was the game changer. The whole thing came to a head in 1893 at the World's Fair, where AC won the contract to power the whole event. That basically sealed the deal. AC became the standard for our power grid. But here's the twist. DC was still way better for electronics, so the world was left with this problem: AC grids and DC devices. So how do we build that bridge? How do we get from the wild AC power in our walls to the clean, stable DC that our devices are thirsty for? Well, the answer is inside that little brick you plug in, your charger. It all happens in 3 really important steps. Let's walk through them one by one. First step, we have what's called rectification. Now, imagine AC power is like a tide. It flows in, then it flows out, back and forth, back and forth. The job of rectification is to act like a dam, stopping that backward flow. It forces all the electricity to move in just one direction. Now, what you get out isn't perfect, not yet. It's more of a bumpy, pulsating current. But hey, it's a huge first step. And the hero that makes this possible? A tiny little component called a diode. Yeah, the diode really is the star of the show here. The easiest way to think about it is like a one-way street for electricity. Or maybe like a bouncer at a club. Current can go in, but it absolutely cannot go back out the way it came. It just slams the door shut. And when you arrange a few of these diodes in a clever pattern, something called a bridge rectifier, you can take that two-way AC traffic and force it all down a single one-way street. Okay, so we've got one-way traffic, but now we have a new problem. That pulsating DC we made, it's still way too rough and bumpy for our delicate electronics. Think of it like a really bumpy road, full of peaks and valleys. Step 2 is all about smoothing, basically paving that road. To do this, we use something called a capacitor. It works like a tiny, super fast charging battery. It soaks up energy when the voltage is high and then releases it when the voltage drops. It fills in the potholes, smoothing out all those bumps into a much more stable, level flow of power. All right, we are so close. The DC power is now way smoother, but there's one last problem. It might not be the exact voltage your device needs. You know, your phone might need a precise 5 volts, while your laptop might demand 20. And giving it the wrong amount is, well, it's a really bad idea. That's where the final step, regulation, comes in. Think of a voltage regulator as a super strict gatekeeper. It's constantly checking the voltage, and if it's even a tiny bit too high or too low, it adjusts it on the fly. It makes sure your device gets a precise, rock-solid, perfect level of power, exactly what it needs to run safely, no more, no less. So that 3-step process, rectify, smooth, regulate, that's the core idea. It's the playbook. But, you know, the first attempts at this, they weren't exactly pretty. Early power supplies had some major issues, and overcoming those challenges is what led to decades of really amazing innovation. Here was the biggest headache. Converting power is just not a perfectly efficient process. You're always going to lose some energy. And where does that lost energy go? It turns into heat. And heat is the enemy of electronics. Too much of it, and you'll fry your components and seriously shorten the life of your device. On top of that, the parts you needed to do this were big and heavy. I mean, if you remember those old chargers from back in the day, they were absolute bricks. And this leads us right to the modern solution. And honestly, the difference is just night and day. In the old corner, you had what were called linear power supplies. They were bulky, they got super hot, they were just inefficient. But now, pretty much every charger you own uses a technology called a switched mode power supply, or SMPS for short. This thing was a total game changer. It tackled the problems of size, heat, and efficiency all at once. So how do these things work their magic? It's actually really clever. Instead of just taking the extra voltage and burning it off as wasted heat, a switched-mode power supply rapidly switches the power on and off, thousands, even millions of times a second. It's like a super-fast faucet, only letting through the exact amount of power needed. This boosts efficiency like you wouldn't believe. And when you combine that with other modern tricks like power factor correction to make it play nicely with the power grid, and incredible new semiconductors that make all this super-fast switching possible, well, that's how we get the tiny, lightweight, and cool-to-the-touch chargers that we all have today. Okay, so let's zoom out and put the whole picture together. Let's trace that amazing journey of electricity, all the way from the power plant, through the grid, into your home, and right to the device you're watching this on right now. It all starts with AC power, traveling super efficiently across hundreds of miles to your wall. Then you plug in your device, and that little adapter, that little power brick, springs into action. Step 1, rectification turns the two-way AC street into a one-way DC lane. Step 2, smoothing paves over all the bumps. And Step 3, regulation makes sure the voltage is absolutely perfect. It's this quiet, hidden, three-step dance that makes our entire digital world possible. And that's really the bottom line here. This isn't just some abstract electronics lesson. It is the absolute foundation of everything we use. Think about it. Every single time engineers figure out how to make this process even a little bit smaller or a little more efficient, it opens the door for brand new technology. It's why our phones get thinner and our laptops get more powerful. So that leaves us with a really interesting question to think about, right? Our devices are only getting more powerful, and we want them to be even smaller and more integrated into our lives. So what does the next great innovation in power conversion look like? What's the next big leap forward going to be? I'd love to hear what you think in the comments. Thanks for geeking out with me on this one.